First, an opening remark on the notion of risk. Risk of a disturbance can be decomposed as by an incidence function and a consequence function. The probability that something happens and the consequences of that thing happening. And this morning we heard a lot about consequences or impacts. And so, ironically enough, this second afternoon session really talks about incidence or probability of occurrence. And so they actually dovetail these concepts of incidence and consequence. They are integrable. This is a map of Alberta showing the progression of the outbreak thus far. We have a pointer up here. Is this a pointer? Okay, so we have a map of the progression of the outbreak. You've seen this last week, so I won't dwell on it. But simply to point out that there are at least two main axes of spread, the northeast axis and then a southeast axis. And these axes of spread are fueled in part by local population growth, but they're fueled also in part by dispersal, long-range dispersal, and arm-like extensions of the range of the mountain pine beetle in particular years. So the cyan color were these populations surging out from this part of BC out towards the Whitecourt region, as far as Whitecourt in 2006. Damage showing up in the summer of 2007. And then later, in the summer of 2009, some early faders appeared around the Mineral Lakes area, and then all the damage associated with that in flight showed up in the summer of 2010. So we've been monitoring this system, or the province has been monitoring this system and doing a great job of monitoring this system. And so you've got 5 years of data here, and over the 5 years that it's been monitored, you had 2 of these long-range immigration events. So, multiple occurrences of mountain pine beetle range extensions occurring as a result of dispersal. And later on we're going to hear about some population genetics data associated with that phenomenon. But two take-home points here. Mountain pine beetle status on the leading edge are different in these 2 areas. You've got this area out here on the leading edge where mountain pine beetle, as we heard, is now in jack pine. It's crossed over. It's now endemic across the Athabasca River right here, just south of Athabasca, heading into Saskatchewan. So what's the spread rate likely to be? What's the impact likely to be? Good question. And then also we heard this morning some commentary from people working down in Sundre in the southern Foothills area, an area where mountain pine beetle is located but is not there in large numbers yet. So 2 big asset baskets that are at risk. And you can see that a little bit better with this map of the BC data, mortality spot data, and then Alberta mortality spot data. This huge belt where mountain pine beetle is not attacking in mass numbers. You have neither mass attacks nor massive attacks happening in this range right here. But when you overlay the population data, the trap tree data, you can see little yellow triangles throughout this matrix of green circles. So you've got a large area where you've got endemic populations situated, but they're not erupting. Also out on the eastern edge, you've got endemic populations south of Fort McMurray, north of Lac La Biche right here. So 120 kilometers. So you've got very different dynamics going on here. An invasive dynamic happening over here, where it appears to be limited by spread, and something else happening here, where it appears to be limited by, well, we don't know what it's limited by, but it could be, for example, there's a lack of source populations and a lack of pine, a lack of attack pine out in BC on the other side of the Rockies. And even through the Rocky Mountain Trench, you can see the Rocky Mountain Trench is a favored place for beetles in southern BC, central BC, and northern BC, going all the way up the Rocky Mountain Trench up to the Northwest Territories Yukon border up here. And but there's a lack of population sources in the Rocky Mountain Trench region right here. So somebody was asking earlier about the lack of population eruptions in this area, and there's 2 things to say there, just backing quickly up one slide. You've obviously got immigration now coming around from the north, and you've got immigration coming around from the south. So this area is being affected by immigrants coming around either end, doing an end run, and presumably not a lot coming across the Rockies here, because there's not a lot of source populations there. But we actually don't know how much immigration there is across the BC-Alberta border in this region. We don't know. It's probably low, but we really don't know. And so, yeah, some of the stuff that people will talk about later on population genetics will bear on that question of what's happening in that area. A very important, I wish it was a paper published, but it's not. It's a working paper, so gray literature, where these guys were studying simulation models of mountain pine beetle spread, and they sadly concluded that after studying the problem for 6 years, their model was failing. So I'm happy that they actually reported that the model was failing, but they observed two problems, the two that I just showed you. Landscape connectivity in the north suggested that those fragmented stands would not be an axis of spread, and then beetles did not travel south from the Kakwa entry area, a likely path according to as late as 07, 08, 08, 09 simulation graph experiments. And these are quotes. I didn't want to not quote them. These are quotes. Further explanation of this phenomenon is required to understand a better model why beetle movement south has been inhibited. Just want to go back to that one slide there and show that this is the fragmented pine where they're spreading very, very quickly through this pine right here, and they're spreading very, very slowly through this the pine basket down here in southern Alberta. So contrary to expectations from this connectivity model.
And just one, where is that Kakwa or Kakwa?
The Kakwa entry area is the part in here, and we do know that there were beetles showing up in very small numbers right within a kilometer of that border in 97, in 99, and then again in 2001. So their model predicted that they would move very quickly along this axis labeled SE, that they should be down here fairly quickly, and it would take a long, long time for them to ever get up to here, and certainly a very long time to ever get past Lave Lake. That's Kakwa, it's that corner right there. So when we started this project back in 2006, we realized that there were an array of models that were being used to model mountain pine beetle risk. We had heuristic risk models, statistical spread models, explanatory models, analytical mathematical models like the type from Logan and Powell. The guys who wrote the initial story on mountain pine beetle, Ghost Force of Global Warming, 2001. So, and down to very detailed models, population simulation models like the one from Safranik and his friends in 1999. So we knew when we started this work that there were a lot of different models out there. There was a lot to choose from, and we knew that genomics could, or we figured that genomics data could inform a variety of models, but these models have different features in them. So at the very basic, these models contain nothing but regionality in them. These other models are a little more detailed, so they've got processes like beetle aggregation, beetle pitch out, and death of first instar larvae from resinosis, and beetle dispersal, down to the really detailed models where there are a whole bunch more processes: pathogenicity, selection, adaptation, tree nutrition, and drought, and the interaction between drought and nutrition effect on tree defenses, and beetle pitch out, and overwintering mortality. So a range of models, and they increase. You can put them on a gradient of complexity. These models down here being very realistic and very detailed, but not tractable from a mathematical perspective, or even from a simulation perspective. So the idea was to say as much as we could about key ecological processes that have a genetic and an environmental component to them. And we really were interested in regional differences resulting from genetics, the issue about dispersal and what population genetics tell us about that, and then especially the overwintering biology, because our early observations in Alberta suggested that that would be a key factor no matter where you were operating in Alberta. So we wanted to really address those three, and what you'll see in the later talks is that we have addressed those three issues. Pretty interesting. We have plans for more work, and this is an example of a kind of thing that we're proposing in a related research proposal, to do an analysis, a formal analysis of the spread data that I just showed you, where we're looking at patterns in time and space, the dependency of tree attacks on attacks on neighboring cells in earlier years as a function of different types of data sets. Some of these data are owned by ESRD, some of them by us and CFS, and some of these are genomics layers owned by the University of Alberta. So it's kind of an integrated epidemiological model, including some of the things that I've talked about, from
climate to genetics to fungal pathogenicity and
dispersal. So there's, we have been integrating and there's plans to do more integrating.